perfect everyone was.
I wonder, like, it's in our notes. What's it say?
It's 5 plus.
People like art class? No.
Okay,
It's 5.
so
No,
yesterday, we were beginning to plot some points in polar coordinates, and everything was going great until we hit problem 1C. And somebody, I can't remember who it is, somebody in here said, wait a minute, you told us that the first coordinate is a distance. How can that distance be negative? Well, we're going to talk about that. So good to see you guys. Precal subs for no one. Come back after school. All right? Okay. They're graduates. And they come back, and I love to see them, but you guys paid for this, so. Our parents are supportive. All right, you ready? So we want to plot the point -3, 60. Now, the reason we need negative R values, polar coordinates are R, theta. The reason we need negative R values is we're going to be graphing equations in polar coordinates, and it's possible that you might have an equation that looked like this. And if I said, all right, do something with this, isn't the first thing that would come to mind is, let's square root it? And when you square root it, you get a positive and a negative. So negative R values happen. So we got to talk about how you deal with them. And it's very, very easy. So certainly I'm going to be on the circle with a radius of 3. When the radius is negative, it changes your angle by 180 degrees. So in other words, you're going to plot it directly opposite 60. And directly opposite 60 would be half a circle, 180 degrees. So this one's going to be plotted at 240. So that point is actually plotted at 3, 240, which would be right here. So a negative R value simply throws you into the opposite quadrant. Easy. That's all there is to it. Mystery solved. All right, number 2. Name all the points plotted at the same place as 2, 100. Now, we kind of talked about this yesterday. Why are there so many ways to name polar coordinates? Because the angles can be named lots of ways, right? So we talked about this yesterday. We could actually rename this angle by doing what? Adding or subtracting revolutions, coterminal angles, right? So we could say 100 plus or minus 360n, where n is some whole number. That would be all of the angles, whoops, not quite, but that would be all of the points with a positive R value. But what about the points with a negative R value? If I want this same point, but I want R to be negative, then what will that starting angle be? It won't be 100, it will be, just talk about it. Change the sign on R, does what to your angle? 180 degrees different. So this is going to be what, 280? And all of its coterminals. Adding 180 or subtracting 180 is exactly the same thing. So if you did negative 180, your angle here would be negative 80, which is the same thing. Yeah. So generally we try to keep it positive if we can. So I added 180, but it would
How would you plot 2 100?
Just raising it, should be like right here, just past the 90. Actually, it'd be farther than that, because this is 105. That's the angle,
Okay.
so in between 90 and 105. Okay, so all of the angles, or excuse me, all of the ordered pairs that plot in this point, at that place right there, all of these plot there. Because if I take 100 and add or subtract 360, I'm in that same spot. If I make my R negative, I'm gonna end up in that same spot. If I start at 280, it backs up 180, which puts me right back at 100. So all those are. All right, convert to rectangular coordinates. So we have a polar coordinate pair, that's r theta. And what are we looking for? X and y. We want to change that into x and y. We want to find x and y. Do you have thoughts on how you might do that? Oh, do the sine cosine thing. So, I want you to think about this for a minute. 2 comma 120 means I'm at an angle of 120 degrees and I am 2 units long. Envision a circle there. Does that make sense to you, that that's what I've got? And I want to find x and y that correspond to that. It's this where I can do without a calculator. If it weren't special, I would use a calculator. But I can do this. This angle's 60, right? If that's 2, this is going to be, oh, I don't know. Yeah, no, yeah, this is going to be 1, and this is going to be root 3.
Yeah.
And that's actually going to be negative 1. So what are the rectangular coordinates, the x and the y, that correspond to that given data? Negative 1, comma, root 3. Now you're going to kick yourselves that we went through all that trouble. I mean, it's okay. But you did this on your quiz. Now, it wasn't worded that way, but on your quiz, didn't I give you a magnitude and a direction and ask you to find the coordinates for that, the components, the x and the y? How did you do it? Who remembers? X equals r cosine theta. Oops. This is r, this is theta. X equals 2 cosine and y equals 2 sine. If you do it that way, and you're doing it on a calculator, now this one I can do by hand because it happens to be 120. But if I use that 120 in my calculator, then my answers are going to come out exactly right. If you use reference angles, remember, you have to remember to put in the negatives yourself, right? So I always say, use the original angle, especially if you're using your calculator. X is r cosine theta, y is r sine theta. Please remember that. X is our cosine, y is our sine. We're going to use that over and over. All right, 3 comma 117. This is a polar coordinate pair. This is r, this is theta. You're changing it to x and y. You don't have a choice. This one you're going to type in. How are you going to get your x? 3 cosine 117. How are you going to get your y? 3 sine 117. And it's assuming you've got your calculator set in degrees, it's all going to turn out just beautiful. 3 cosine 117. Negative 1.36. And 2.67. hard is it to change from polar to rectangular? Not hard. Not hard. All right, now we're gonna go the other direction. Now we're gonna start with X and Y. And we're gonna find R and theta. All right, any ideas how we might do this?
You could find.
We could draw that picture.
Yeah.
Because if you go over 3 and down 4, doesn't your triangle look like that? Isn't this R and this is theta? Standard position. So R is gonna be 5. And how are we gonna find theta? Second tangent, 4 divided by 3, and then subtract that from 360. So 306.87. There is no rule with polar coordinates. Now we're going to talk about something called polar form later on. In polar coordinates, theta can be negative. So if you would rather say negative 53 point whatever, totally fine. In polar form, theta's gotta be positive. So I just am in the habit of always using positives, because in polar form, it makes a difference. Here it doesn't. So if you said negative 53, that is absolutely fine for this problem. All right, what about negative 5.1? That's your X and Y. We want our R and theta. So let's draw a picture of negative 5.1. What's my radius or my R? 26. And this is your theta, so be careful. That's your theta. So second tangent, 1 divided by 5. And subtract that from 180. Do you get 168.69? Like always, your angle has to be in standard position. So make adjustments to whatever quadrant you're in, based on whatever quadrant you're in.
Is it, I put mine in with the negative and should I have not done that because I got it completely different
Okay,
answers?
I don't want to say it. It doesn't matter so much if you tangent, you would just get negative 11.
And you don't Yeah,
But you need to know how big that angle is. That angle is negative, that angle is
Oh, so
You're looking for this angle here, right here.
yeah.
Yeah. All right. These are definitely polar equations. We know they're polar equations because their variables are R and theta. This would be a rectangular equation because its variables are X and Y. So your job is to take this polar equation and change it into a rectangular equation. Always when I'm doing this stuff, I have this little triangle in my mind. This is theta in standard position. This is X, this is Y, and this is R. That picture ties everything together. It shows me X and Y, and it shows me R and theta. And it's kind of what we did right here. Here was my X and Y, there's my R, and there's my theta. Okay, so tell me about cosine theta. You can either use the picture or you can remember what you memorized. What's the cosine of theta? X over R. So R equals 4 times X over R. Every trig function, whether it's cosine, cosecant, sine, every trig function can be expressed as something from the triangle, right? Opposite over adjacent, hypotenuse over opposite, whatever. You can always replace your function. Now, let's look at that equation there. It has a fraction in it. How about if we multiply that fraction out? Then it's going to say r squared equals 4x. Now, look at your picture. What can you tell me about r squared?
X squared.
It's x squared plus y squared, isn't it? So that r squared is going to become x squared plus y squared equals 4x. What are the variables in that equation? Cartesian. That's your Cartesian equation. Anybody know what shape that is? You should know. That's a circle. So this right here is the polar form of a circle. You don't need to memorize that. Okay, let's do the next one. Do exactly what we did up here. What are you going to do first? What's cosecant in terms of your memorized things, or look at the triangle? Cosecant is r over y. Now what? Get rid of the fraction. So ry equals 3r. Now that looks a little different. Would you go into some kind of spastic attack if I did this and said y equals 3? No. Now, normally I would. Normally, if you divided by r, a variable, I would be freaking out. Why is it okay?
It can't be
R is
0.
not going to be 0. What happens if r is 0?
It's not a triangle.
You're at the pole, right?
Yeah.
You're just right there at the pole, so you're going to have a problem to deal with. So you're allowed to divide by r. Can you divide by theta? Can you divide by theta? No, because can theta be 0? Isn't it 0 all along here? Yeah, so you're not dividing by theta, but you certainly can divide by r. So believe it or not, this equation is what? What is that? That's a horizontal line. And in a little bit, we're gonna graph it, and you're gonna see that it's a horizontal line. Okay, what about this one? This one looks a little more challenging. What do you want to do with it? So change your functions. So r equals 2y over r minus 4x over r. Multiply out the r's. So we have r squared equals 2y minus 4x. And what's r squared? X squared plus y squared. And that, my friends, is another circle. It's not centered at the origin because of all that adding and subtracting that's going on, but it is definitely a circle. Wow, this is pretty easy. We're gonna go to our calculators in a second, but first we gotta do a couple more sections. Write as a polar equation. Believe it or not, this is even easier than that was. A couple minutes ago, I said, I want you really, really, really to try to remember something. What did I tell you to remember? X equals r cosine theta. So x is r cosine theta. What are the variables in that equation? R, and theta. Am I done? Yes, I'm done. My job was to make it a polar equation. I've done that. Took out the x and replaced it. All right, what about B? 2x minus 3y equals 5. You're making that, that's Cartesian right now, that's a line. You're making it polar. Overthink it. 2 r cosine theta minus 3 r sine theta equals 5. When I graph in polar coordinates, you know how when you graph, like if you were gonna graph this on your calculator, that's rectangular. But if you were gonna graph that on your calculator, what would you have to do to it? Get y by itself, right? You just have to rewrite the equation. If you're graphing in polar, you have to get r by itself. So this equation is absolutely 100% fine, but if I'm gonna graph it, I'm gonna have to manipulate some things and get r by itself. Like factor out the r and divide by everything, so r will equal 5 over some stuff. That's how I would graph it on my calculator. But this is a polar equation. We are finished. One more. What polar equation is this? Well, it's gonna be a circle, I can tell that rectangularly, but what's gonna be the polar form of that? Any thoughts on how we might proceed? Your job is to change that into an equation that has only r's and thetas. So no more x's and y's, we gotta get rid of all that. What do you think, Allison? You can pull it out? Okay, so she says go ahead and multiply it out. So x squared plus 6x plus 9 and y squared plus 6y plus 9 equals 18. Okay, that's perfectly okay. There is absolutely nothing wrong with that. Okay, what do you notice about that?
The 9 that's okay.
All that's gonna go away, okay. So x squared plus 6x plus y squared plus 6y equals 0. Okay,
Can you transfer all variables?
they're already on one side.
When
is
they're
that what
like
you
the
said?
x's and the y's.
Okay, now, let's look at something. What's this? What's that part? R squared? So let's just deal with that. So that's gonna be r squared. Now, what about that? Plus 6 r cosine theta plus 6 r sine theta. And now we have our polar equation. If we hadn't foiled, and I don't know, maybe that occurred to all of you to foil, it's great, worked out great. If you didn't foil, if you did your substitution here, it still would have worked out okay. Because what you would have ended up with, part of your terms, would have been r squared cosine squared and r squared sine squared. But cosine squared and sine squared makes 1, so you would have been just left with your r squared, even if you did it foiling up there. This worked out great, thank you, Allison. All right, one more section and we're going to our calculators. And we kind of already did this section, so this should be easy for you. It says, find polar coordinates. So this is x and y. We're finding r and theta. Only they're stipulating that theta has to be between 0 and 2 pi, which means in radians once around, which means you're not going to be doing the plus or minus thing, right? And R has to be positive, so they're being very specific about which point you want. So we need R and theta, and our point is 1, 2. So what is R? Square root of 5. What is theta? This is gonna be theta right here, right? Calculator's gotta be in radians, because that's how the problem is. And we're gonna do second tangent 2. I got 1.11, did you? Now there are lots of other ways to name that angle, but I'm not sure any of them meet the criteria, because what would happen if I went this way? I could name, this is 1.11. I could go this way, right, and name that angle, but what would be wrong with doing that in this problem? It's not between 0 and 2 pi, it'd be negative, right? I could have a negative root 5 to name that, but that would not meet this criteria. I think that's our only answer, isn't it? Isn't that the only angle, or the only way to name that point that has a positive R and a theta that's within the first revolution? Yeah? Okay, next. New point, negative 1, 5. But this time, I'm still between 0 and 2 pi, but R has to be negative. Now, that point is where that point is. So negative 1, 5 is right here. I don't care how you name it, it's not changing, that's where it is. What's its radius? Square root of 26. So my first stab at the problem is gonna be root 26, comma, this angle. This is not my answer, this is step 1. The radius is root 26, the angle that corresponds with that is second tangent 5, subtracted from pi. Second tangent 5. There we go. Subtracted from pi. I got 1.77. Is that what you got? Now that is right. There's nothing wrong with that, except the directions said that for whatever reason they want the angle to be, or excuse me, the radius to be negative. So I'm going to go ahead and make my radius negative, and then how does that change my angle? By 180, not by 2 pi. 2 pi would put you in the same spot. You're going to the opposite quadrant, so you're adding 180 or subtracting 180, except I'm in radians, so I'm adding pi or subtracting pi. So think about it, 1.77. To keep it positive, am I gonna add pi to that or subtract pi from it? I'm gonna add it, and I got 4.91. And there is the answer to that question. Okay, 4.91 is down here, and that makes perfectly good sense, because when the radius is negative, you go to the opposite quadrant. So I've got to get into quadrant 4, since my original was in quadrant 2. All right, one more. This one is crazy. This one is crazy. All right, so here we go. These are the rules. Our point is 1, -3, which makes my radius √10. And I'm gonna go ahead and find my reference angle. I know this isn't gonna be my answer, but go ahead and find it. Second tangent 3. So that reference angle is 1.25. In standard position, that angle would be 5.03. So if I were walking down the hall and I found this rectangular pair, and I don't know, one of Miss White says, change that into polar coordinates. This is what I would change it into. Okay? Does that fit what I've been told? I've been told that my angle has to be between -3.14 and +3.14. Is it? No. So I'm gonna have to change that angle. I've also been told that R can be positive or negative. Okay? All right, so let's start with the angle part. I'm gonna leave this √10. But instead of doing this angle, what if I did this one? -1.25. Would that work? Is that between where I need it to be? Okay, so there's an answer.
Would you
Now.
subtract 2 pi?
What? I just used my reference angle negative.
Oh, yeah.
Now, what if I made R negative, because it says I'm allowed? How is that gonna change this angle right here, if I make R negative? What's it gonna do? I'll add pi to it. Okay, so I'm gonna take that number, -1.25, and add pi to it. Does that keep me within the boundaries that I'm supposed to be within? Okay, so that one works. Now, am I gonna be allowed, remember, I can add or subtract 2 pi and not change this point. Would adding or subtracting 2 pi to either of those keep me where I need to be? Nope, these are it. Those are my two answers. I have one positive and one negative within those boundaries. All right, the moment we've been waiting for. Use your grapher to match the polar equation with its graph. All right, so here we go. We're gonna graph, so go to mode. And we have to change our mode into polar. Polar, P-O-L. When you press Y equals now, it no longer says Y equals, it says R equals, which is how we put them in. So let's just do the first one. Oh shoot, it's a cosecant, but that's okay. How do I put a cosecant in? It'll be 5 divided by sine theta. And your theta is where your X was. It's your variable button. Now when you press it, you get a theta. Remember, in parametric, you get a T. In rectangular, you get an X, and polar, you get that. Now, I have no idea how your window is set. Let's take a look at that real quick and see. Let's go to window. Guys, how you set this up is going to depend on whether you are in degrees or radians, because you're putting in an angle, sine theta. I am in radians from the last problem, so my theta min is going to be 0, and my theta max is going to be 2 pi. I'm going to go once around. There's no point going more than that, once around. I'm going to use for my x's, my x and y, and somebody asked me, Mrs. Ford, I thought we were in polar. We are, but what's the shape of my screen? It's a rectangle. We can't get away from telling the calculator how big to be. So I'm just gonna go from -10 to 10 and see what happens. Now, how is your theta step set? This is important. What is your theta step set as? Mine is 0.13. You got 0.13? Perfect. If it's not 0.13, make it 0.13. We'll talk about it in a minute. All right? Now, let's hit graph and see if we get a shape.
I got a line.
You got a line. What kind of line?
Just
Horizontal.
You got a horizontal line, which means if I were to write this as a rectangular equation, it would be like y equals.
Yep.
Now, real quick, just to remind you, the equation was 5 cosecant, so it's r equals 5 cosecant, which is y over r, excuse me, r over y. So when I multiply by y, and then I divide by r, do I get a horizontal line? It's exactly what you expected, a horizontal line. Let's try another one before I answer Marin's question. 32, r equals 4 sine theta. Don't change a thing, just type in your new equation. 4 sine theta. Did you get something that looks kind of circular sitting on top of the x-axis? Okay, hit zoom square. Zoom square is 5, zoom 5.
Oh, circle.
That squares your screen and that shows you a circle. This one is a circle. Okay? Now, how long did it take to graph that? It came up real quick, didn't it? I want to show you something. Go back to your window and set your step at, let's say 1. Theta step. Just set it at 1 and hit graph.
Oh.
Wait,
Oh, it's like the Doritos
that's not
logo.
too good. Okay, all right, we're gonna talk about that. That's wacky. All right, go back to window. Set theta step at 0.001. 0.001. And hit graph.
Oh, it's tiny. Oh, it's taking forever to get so look. Oh, it's taking forever.
Why is it taking so long? It is graphing, guys. It's going to graph, but it's going to take so long. Here is what's happening. Your calculator graphs just like you do. You graph by plotting points. Theta step is the distance between your theta. So when I set it at 0.001, it's plotting a point at 0.001, 0.002, 0.003, all the way to 6.28. How many points is that? So many. Okay, when we set it at 1, remember our max is 6.28. When I set it at 1, it plotted 1, 2, 3, 4, 5, 6. Why did your picture turn out so jaggedy? Because that's not enough points. That's not enough points. So what does theta step control? How many points you are plotting. If you're going from 0 to 6, 0.1 is a good number. If you're going from 0 to 360, if you're in degrees, then I wouldn't use 0.1. It's going to take forever. So your step is going to depend on your minimum and maximum theta. In radians, I would use 0.1. In degrees, I would use 5 probably at the minimum. If your picture turns out jaggedy, make your step smaller. If you're still graphing 10 minutes after you put it in, make your step bigger. Okay? All right, let's do the rest of them real
I
quick
didn't
here.
get out of this.
You can second quit, usually that works.
Oh,
I mean, eventually it's gonna be done.
Mine's frozen.
All right,
There we go.
number 33.
Mine's
All right, I'm gonna change that step back before I hit graph again.
Has anyone been able to get out of it yet?
It took
It
like
takes
5 minutes.
Okay.
Hit the on and off
Yeah, you can just turn it off or, okay, R equals 4 cosine 3 theta. So R equals 4 cosine 3 theta. Now that parentheses is gonna come up, that 3 theta has to be in parentheses. It comes up on your calculator automatically. Hit graph. Go ahead and zoom square if you're not already. And you get one of the pictures there. It looks like we get, C. We're gonna talk about this a lot right now. First, we have one more to graph, 4 sine 3 theta. So look carefully, before you go to the next one, look carefully at what happened with 33, and now graph 34. Don't do it together, it'll be way too messy.
I like if you do them together.
Anybody have a spirograph when you were a little kid?
Yeah.
Didn't you get this, couldn't you get this kind of stuff with the spirograph? Because wasn't your spirograph a bunch of circles, like little circles that you did like gears around? That's a polar, spirographs was your first exposure to polar coordinates.
I've been doing this since I was
Okay.
3.
It's like, you know, you
Mine's just not graphing.
Now, wait now. Okay, I will right after class. Okay, now, we need to talk about this. First of all, the last two things we graphed, the equations were very similar. And so were the pictures. What was the difference in the pictures? What?
Rotated.
Rotated. All right, now stop a minute. This is all gonna tie into what we learned before. What was the difference between a sine graph and a cosine graph? In a rectangular system, weren't they exactly the same, but shifted? So in a rectangular system, they were shifted. The same picture, same curve, but shifted. Put that in a circular system, and you are rotated. So the only difference between, graph some weird sine thing and some weird weird cosine thing is going to be a rotation. All right? Second thing, there is no coincidence, and this is maybe hard for you to see. Can you tell me how long that shape is called a rose? That's the first of your classical curves. We're going to list the classical curves down at the bottom. The rose, can you tell me how long those leaves are, or how long those petals are? They're 4 units long. That is not a coincidence. I want you to think back, when we graphed 4 sine x, what happened? The amplitude, the height of the curve became 4. Well, in the circular system now, it's not the height anymore, it's the distance it is from the pole. So those leaves are now 4. Put a 3 in front of that equation and they're going to be 3. Put a 10, they're going to be 10. Keep that in mind because that kind of helps you set your window for some of your future graphs. Okay. Now, how many leaves do they have? 3. That's probably not a coincidence either, right, from the equation? But before you get too carried away, go back to whatever equation you got in and change that 3 theta to a 4 theta. No, you don't. Now, when you put a 4 theta in there, you didn't.
Can't tell my quality's terrible.
It's a rose, but there's 8 of them. There's 8 of them. Wait a second. So when we graph 4, are you doing cosine or sine? Probably sine. It doesn't matter. When you did 4 sine 3 theta, you got 3 leaves.
It does look like that.
But when you did 4 sine 4 theta, you got 8 leaves. All right, let's try 5 theta. Do 4 sine 5 theta.
Wow, wait. I got like 10.
No, it's not 25. 5. So when we did 4 sine 5 theta, you got 5 leaves. I don't know. Sydney says, is 6 going to be 12? Let's try it. R equals 4 sine 6 theta.
Wait.
Wow, it was just like a sun.
Now, when you're graphing that many leaves, you may need to make your step a little bit smaller so that it plots a few more points, but you should be getting 12 leaves. Okay? So what? So 7 would be 7. So what seems to be the rule here?
Even if it's double.
This number is always going to be the length of the leaves. No matter what, that's the length of the leaves, the amplitude. This number tells you how many leaves. If it's odd, it's that many. If it's even, it's
Double.
twice that. Okay? So odd is that many, even is twice that. So I can see a quiz question or something. R equals 8 sine 14 theta. What shape is it? It's a rose. This is the format of a rose equation. How long are its leaves? 8. How many are there? 28. Because that number's even. If this were a 13, it would be 13 of them. All right, that's our first classical curve. All right, we're gonna do one more today. I want you to type it, first of all, what is your window? I need to know what the window is, make sure we got that set right.
-10 to 10.
Okay, let's shrink that up. Let's make that -5 to 5 on X and Y. We're in radians, so theta should still be 0 to 2 pi with a step of 0.1. All right, got it? All right, I want you to type this in. Okay, first of all, guys, it is not a rose.
Like a fat heart.
A fat heart.
Look at it, bigger. Some of it's not fat heart.
I don't think that looks like a heart.
What does it look
I
like?
feel really bad with
I don't know
It's
what kind
funny
of
she
heart.
would say that.
These are
Did you get a picture that looks
That looks lovely.
like this? Oh, not like that. It looks like this. Something like that. This shape, remember, this shape is a rose. So we have 4 classical curves. The classical curves are the main shapes studied by the Greeks back in the days. There are lots of other shapes, but the 4 main ones, the basic ones, we got the rose. This is called a limacon. I remember that because that looks like lima, which makes me think of lima beans, which look kind of like that.
not hard.
Now wait, we're getting there, You just hang on a minute. Now, everybody okay with that? That's a limacon. Now, change this to a 2. So just change
Nobody
that
tell me what
one
happened.
It's gonna be hard. It's gonna be
number to a 2.
2 cosine.
Oh, it is so good.
That looks like a heart. That one.
Isn't that
That looks like
That is
a
like-
word.
Now, zoom square it, and you get her heart.
No way.
That's her heart.
Aww.
This curve,
So cute.
2 plus 2 cosine theta, and remember, it'll work with a sine also. What's the only difference that's gonna happen if I change this to a sine? It's gonna rotate. This right here is called a cardioid. That is its actual name.
Wait.
It's a heart shape. Now, what makes a limacon a cardioid? These two numbers have to match. If those two numbers match, then you're going to have a cardioid. Now, a cardioid is a special limacon. So this is still a limacon, but it's a special limacon because the numbers match. Furthermore, the absolute value has to match. So this could actually be a minus, and it's still a cardioid. So if these two numbers have the same absolute value, then you have a cardioid. Real quick, do that one and see what happens. What happens to the graph when you do 2 minus 2 cosine theta?
Oh. Little bit of form.
It's like flip-flop. Does that sort of make sense, knowing what you know about minuses? Kind of makes sense? Yeah. All right, that's enough for today. We covered a lot of ground. Next time we are together, we will discuss the other 2 curves.